Hi, everyone. In this video, we're going to apply our theorem from the last video, which stated criteria for when we can expect an Euler path or an Euler circuit to exist on a graph. And the way we did that, just very briefly, was we looked at the degrees of each vertex. So our theorem told us that we have an Euler circuit if and only if that we're both connected and all of our vertices are even. And we have an Euler path if and only if we are connected and all of our vertices have, or we're connected and we have exactly two odd vertices, okay? So we just need to check if it's connected and see, look at the degree of each vertex and see what we have, okay? And so we saw that our original graph using, for the Königsberg bridges problem, that did not have an Euler path or an Euler circuit because we had too many odd degree vertices. And so we have a couple of examples here. We're just going to go through and see whether or not we have an Euler path, an Euler circuit, or neither. And then see if we can try and find one. Okay, so we're going to begin by making sure, is this connected? So one trick to do this is pick a vertex, say A, and say, do I have a walk from A to any other vertex? So I've got to walk from A to B, like that. I've got to walk from A to C. I've got a two-step walk from A to D. And then I can walk from A to D to E or to F. So I am connected. And so now we want to list the degree of each vertex. So the degree of A, well, we have two edges connected to it. So that's going to be 2. Degree of B, we have 1, 2, 3 edges connected to it. So that's going to be 3. So we already know we do not have an Euler circuit because all of our edges have, or all of our vertices have to be even, and we have an odd vertex. But we still might have an Euler path. The degree of C, that's going to be 2, same reason as A. Degree of D is also going to be 3. 1, 2, 3. The degree of E is going to be 2, and same with the degree of F. Okay, so we see what are our odd vertices. We've got 2 odd vertices, B and D. So we have exactly 2 odd vertices. And so that tells us that we have an Euler path. And so remember, an Euler path always starts on one of the odd degree vertices and it ends on the other one. So every Euler path on this graph starts at B, our first one, and ends at D, our second odd vertex, or starts, or the other way around, starts at D and ends at B. Okay, and in fact, and we'll see, not in this video, but we'll see how to find these Euler paths. One such path goes from B to A, to C, to B, to D, to F, to E, to D. And so we've got B, A, C, B, D, E, F, D. So we start at B and end at D. We could also do this exact same Euler path in reverse, and we would have a path that starts at D and ends at B. Okay, there's many different Euler paths that may exist. Now here, again, I'll let you check that this graph is connected. And we've got, now we go and look at all the degrees. So the degree of A is going to be 2. Degree of B is also 2. The degree of C, this is going to be 1, 2, 3, 4. So degree of C is 4. So far, we're still good because all of our vertices have been even. Degree of D is 1, 2, 3, 4. And degree of E and F are going to be the same. They're both going to be 2. Okay, and so we see, so I should write this is connected. Again, I'll let you verify that. All vertices are even, and so that tells us by our theorem that we have an Euler circuit. And when we have an Euler circuit, it doesn't matter which vertex we can start on. We can start on any of them. And so one such Euler circuit starts, if we start on, say, E, then we could do E to D to F to C. Oh, sorry, that's wrong. We could do E to C to A to B to D to C to F to D to E. And so we start and end at E. So that was, for one example, is E, C, A, and then B, D, C, and then F, D, back to E. So that's E, C, A, B, D, C, F, D, E. And again, we've repeated vertices here. We've repeated C and D and E. That's fine. We just haven't repeated any edges. And so that's good. Okay. So here we have an Euler circuit, and we can start, and there's many, many, many Euler circuits on here. We could start at any vertex. Here. So I will say, so let's look at the degrees. So the degree of A is 2. The degree of B is 2. All the degrees of all the vertices are going to be 2. Everything has degree 2, but it's not connected. Okay, and so this is one of the ways we can fail to have an Euler path or circuit, right? If I'm starting on this left component, if I start at B, then I can hit all the edges on this side, but I have no way of getting to the edges on this component. I would have to invent another bridge or invent another edge. So it's not connected, and so that tells us that there's no Euler path or circuit. Okay, last one. And I encourage you to do this, to pause the video and do this. You can unpause and we'll do it together. So I'll assume you've tried to do it. Hopefully you have. Let's just check, is this connected? Well, can we get from A to any other vertex? I can get from A to B. I can get from A to C. I can get from A to D. I can get from A to E. And so, yeah, I can get from A to any other vertex, so I am connected. So now, just like before, we'll start listing the degrees. So the degree of A is 2. Degree of B is going to be 4. Degree of C is going to be 2. Degree of D is 4. And the degree of E is also 4. 2. Okay, so all even. So we have all vertices are even. And so our theorem tells us that we do have an Euler circuit. Okay, and just for fun, one such Euler circuit is this. Okay, so that's A, B, C, E, D, E, B, D, A. So A, B, C, E to D, back to E, to B, to D, to A. So we hit everything exactly once. Okay, so that's going to be all for this video for examples. The one thing I'll say is, like I said before, this theorem is very, very nice. It tells us exactly when we can expect or when we have an Euler path or an Euler circuit. What this theorem does not do, it does not tell us how to find one if we do have one. Okay, and so we're going to need something else. We're going to need a different tool that we will not cover in this video, but this tool that we're going to be talking about isn't the easiest thing to do. It's not super hard, but it's not the easiest thing to do. So it's nice to know um, whether or not we have an Euler path or circuit before we go through the effort of using this other tool. But we'll talk about that later. That's all for this video.